Do you post these videos to YouTube too?
Yep. Mhm.
Okay, cool. Thank you. Have a good evening.
Thanks, you too. Hey guys.
So right there, yeah, actually, it's actually cool.
Let's don't get about it. Don't get about it. Don't get it.
Yeah.
Don't get it. My bike so I can go.
I can just get whatever you want. I know, like.
If someone influencing that much to do something, people would have their own opinions.
Yeah.
Or other
I'm not one of them. I'm not even like later on they have story came to like talk.
Whatever it is. Maybe like those are the instances. You don't want to do a lot of workshop tools. You can train it anywhere. So don't. Still, go over to that. See what happens. Yeah. Yeah. Show me that.
So, Professor, I have the question for the last question. The very last one. So you showed the answer.
Yeah.
I tried to redo it, but I don't know why I couldn't. So I combined this one is parallel.
Yeah.
And then three of them are parallel.
Yep.
And then all of them is series, so that's why I combined all three of them.
Yep.
Yeah, I did that, but the answer is not.
Let me see. What I might have done in my, because I always go from the back to the front.
Yeah.
I might have combined these two in parallel first, combined that in series with 5, and I combined that in parallel with these 3 right here.
Oh, okay, I see. Yeah,
I need to double check. That's
Yeah.
that's what because I always go from the back to the front. That's usually what.
So because I don't exactly like you, but I did different. I combined it to become the 6 and 7 together, and then all three of these combined to one.
Yeah, I think because you always go from the back to the front. So I would combine these in parallel first, combine that in series. So you have an R 5, 4, 5, 6, 7, and then you combine that in parallel with 3 and 4.
Oh,
And then you
okay.
add
Yeah,
that
maybe
to
maybe
one.
you did that.
Yeah, give that a try and then let me know.
Yeah, because the second one is like just simple, just combine these.
Yeah.
And then,
Yeah.
Okay. I just follow your step and fix just see.
Yes. Sorry.
Professor, for the midterm is based on the homework 1 and 2.
It's based on the most recent homework and then the lump parameter homework.
That was the one with resistance, right?
Yeah.
Oh.
Yeah. I forgot the exact numbers. I'm gonna look at the exact homework.
You're gonna go over it.
Yeah, we're gonna talk about today.
And then Thursday gonna be like a study day or just another?
No, so Thursday we're gonna do like a workshop.
Oh.
I don't learn how to run simulations in vascular. Yeah. So it's important for your final project.
Oh,
So the midterm is primarily based on homework 2 and homework 3.
Okay.
Yeah.
Yeah.
classic.
It's because we're not past 4 yet. It's exactly 3:59.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. All right, so today's an exciting day. So we have a lot to talk about today. So hopefully everyone got my email earlier today. So we have a midterm next week. So we're going to talk about that first thing today. We have a final project. Well, the project that you guys knew was coming, but now the information is posted there. So we'll talk about that as well. And then we have a short lecture today on CFD. So we're going to go over a lot today. Mostly, about kind of the exam, I should say. It's an exam. It's kind of a pseudo final exam. And the final project. So yeah, we have a lot to discuss today, but you know, we'll get through it. All right, so the plan for today, plan for this week actually. So for on Thursday, we're going to be doing a Symbascore workshop. And so if you think back to a few weeks ago, you know, we did the first workshop where, you know, we learned how to create a model in Symbascore. So we did the pathing, the segmentations, and the modeling. On Thursday, we're going to learn how to do meshing and simulations and boundary conditions. And so basically what you need to do for your final project. So the way the workshop is going to work on Thursday is I'm going to upload a kind of like a pre-made project for you, just so that we can all kind of be on the same page. And then what you'll do is that you'll apply what we did on the workshop to your project. You'll run a few different simulations and you'll write your report. And so that'll be it for that. Okay. All right. Any questions I can answer before we get started for today?
We just have the midterm and then the final project. Right?
Exactly. Yeah, no final exam.
Do we have any more?
No, so I don't have any more homework planned. So the only things you'll have left to do in this class is just the exam and the project. Yep, we're getting ready to wrap up the semester. So, all right, any other questions? Okay, all right. So first thing today, let's talk about the midterm exam. I call it a midterm because it's not taking place during finals week, but it's, you know, it's the only exam we're taking in this course, so it is pretty comprehensive, right? Okay, so hopefully everyone got my email today. So I sent an email, you know, earlier today about our midterm exam that's going to be next Tuesday. Okay, so this is just the text of the email, and so, you know, we'll just kind of go through it just quickly now. Like the email says, the midterm is going to be on Tuesday, April 23rd. It's going to be during the lecture and it's going to be in person. So first thing is that, you know, I don't have any plans to offer the exam virtually. So, you know, please plan to be here in person for that. Okay. The exam will cover everything that we covered up to this point in the class, but the emphasis will be on mostly the recent material. So that's some lump parameter modeling, 1D equations, and impedance, right? So the stuff we were covering kind of the few weeks before spring break, up until that point. Okay. In terms of the other stuff, in terms of all the other content that we covered, you can expect a couple conceptual problems on things like medical imaging, arterial biomechanics, and cardiovascular diseases. But again, the vast majority of the stuff is going to be on the recent stuff. Okay. So I did post a study guide, and so this is available for you guys to download on Canvas. So you can access it through, you can access it through the website. And this kind of outlines everything that you need to know for the exam. Now, it is a lot of stuff. I realize that, but remember, you know, mostly what's going to be on the exam is the recent stuff. Okay, so you can see I've broken down the study guide into the different topics. You know, it kind of goes roughly kind of week by week, but it's kind of more roughly just grouped by the topics. But the emphasis is going to be starting on lump parameter modeling. So lump parameter modeling, cardiovascular diseases, 1D equations, impedance. Okay. So you can expect probably like 85–90% of the exam to be on mostly that stuff. But you should have a good grasp of the concepts before that as well. Okay. All right. So the most important part, about 60% of the exam is going to be based on problem solving. And so these are going to be problems like your homeworks. So we've had two kind of major homework assignments in this class. We've had the lump parameter modeling homework, that is homework assignment number 2. And then we had the most recent homework assignment that you guys are working on right now, which is homework 3, which is based on 1D equations and impedance, or in other words, resistance. Okay, I would definitely study the homework assignments, and so you can expect the exam problems to be very similar to what you have on the homeworks. Okay. Of course, you know, there's going to be no MATLAB on the exam. It's going to be all done by pencil and paper. So just kind of focus on what you can do with pencil and paper on those homeworks, and then study the concepts, and you know, you should be good to go. In terms of what you can bring for the exam, it's going to be pretty standard fare. So you can bring a writing utensil, of course, a pencil, a pen. You can bring a calculator. Calculator will definitely be useful for the resistance calculations. And you can bring a cheat sheet. So you can have one 8.5 by 11 sheet of notes. You can write it, you can type it, you can write it, you can go on both sides. You know, it's just limited to just one 8.5 by 11 sheet. Okay. All right, any questions on the midterm exam? Okay. All right, and so that's question in the chat. Question, how many problems can we expect for each section, conceptual and problem solving? So for conceptual questions, there's going to be 5 short answer questions in total. So those are going to be based on all the conceptual learning objectives up here. So you can probably expect, you know, three short answer questions from all the recent stuff, and maybe 2 short answer questions from some of the more beginning stuff. So that'll be worth about 40% of the points, and then there will be 3 problem solving questions. Each of those problem solving questions is going to be worth 20% of the exam, and you can expect 1 from lump parameter modeling, 1 from 1D equations, 1 from impedance. Yeah, I have it visualized in my head. I just haven't written the exam, but that's kind of what I'm thinking at this point. All right, any other questions on the exam? Okay, all right, so that is the exam. A sneeze almost came out. Okay, so let's talk about your final project. There it is. Okay, thank you. All right, so the other thing I posted today is information on your final project. Okay. Or I should say it's kind of part 2 of your midterm project. So, you know, everyone turned in their midterm project last Friday, which basically just included the geometry of your model. Okay. And so the final project, what you're going to be doing is you're going to be running a simulation on that model. So you're going to be running computational fluid dynamics CFD on the blood flow in the model, and then writing a report. Okay. So the due date for the final project is going to be Monday, May 20th, and so you have a little bit over a month to work on it. So that means that you have this is going to be due after finals week. So finals week is the week before this, and so it's going to be May 13th to May 17th, and so it's going to be due the Monday right after that. Okay, just because I know you guys are usually, you know, everyone's busy during the finals week, and so you know, I want to give you a couple extra days after finals week to kind of finish things. Okay. Question: will solutions to the homework problems be uploaded? Yes. So after this this homework assignment is due, I believe this current one is due Wednesday. I'll be posting the solutions for that on Canvas, so you can use that to study. Yeah. Okay. So the final project. So final project is to run a simulation, right? So everyone at this point has created the geometric model for their final project. So the next step is to run a simulation. Okay. So on Thursday of this week, we'll be doing a workshop together about, you know, learning how to run a simulation in Vascular. So part of that will be we'll be learning about meshing, we'll be learning about boundary conditions, running simulations. Okay. And then you'll be doing that for the final project. Okay. Okay. So we'll go over most of these details on Thursday. So I don't want to get too much into it today, just because I want to talk about CFD. Okay. But just to give you a little preview, you are going to be using a supercomputer. So the simulation that you'll be running for this project is a little bit too expensive to run on home computers. You know, even the more powerful ones, and so you know, everyone's going to make an account on this supercomputing gateway, and you'll get a chance to run your simulation on there. Okay. It sounds more exciting than it actually is, but you can at least, you know, maybe cross it off your bucket list of, you know, run a simulation on a supercomputer, and add that to your. You can't really add it to your resume. You know, it's not really you know, I've developed this gateway to make it relatively easy, so you're not going to be using any Linux terminals or anything like that, but you'll at least get to use it once. Okay. Okay. So we'll go over all these details next time, but you know, I wrote them here just so that you can have them. Okay. Okay, but I want to get to this part here, right? So after you run your simulation, you know, you're going to get a figure, right? You're going to get several figures, but basically you're going to be able to tell, you know, what the fluid mechanical quantities inside your model are going to be. So that includes the velocities, the flow rates, the pressures, the shear stresses, and so on. Okay. And so the idea with the final report here is to take your results, you know, take the results of the simulation, combine that together with, you know, the knowledge that we've learned in the class in terms of, you know, how these things are correlated with disease, what these quantities actually mean, you know, pressure drops, shear stresses, things like that. And then you know, do a little bit of analysis, a little bit of a discussion of what that means for your particular patient. Okay. So all of you, you know, when I sent you guys the image data for your final project, there was a PDF report that came with it, right? And so that PDF has a little bit of information about what that patient is, or for some of you, what that animal is. Some of you have bunnies, okay? And so what you're going to do is you're going to correlate the simulation results with the patient, right? So for many of you, that means that, you know, the model that you have contains some kind of disease, whether it be like coarctation or an aneurysm. Some of you have perfectly healthy patients as well. There's actually quite a few healthy models as well. And so, you know, you're going to use the results of the simulation to comment on kind of the cardiovascular health of this patient, okay? And so, for instance, you know, you're going to plot things like the pressure distribution. So you're going to plot how pressure is distributed throughout the model. You're going to answer some discussion questions about that in terms of what the pressure looks like, what that means for the patient. If you have something like a coarctation or an aneurysm, what you're going to see is that you're going to see a very interesting kind of pressure behavior going through the disease. Okay, so you're going to comment on that and kind of say what that means. You're going to do the same thing for the wall shear stress. And so the shear stress, remember, is kind of the frictional stress that the fluid imparts on the vessel wall. And so that is correlated with a lot of other diseases as well. So you're going to comment on that. You're going to look at the velocity streamlines. And so that's going to give you an idea of what the velocity patterns inside your model look like. Okay. As well as one other figure of your choice. Okay. And so depending on your particular model, maybe there are certain areas of interest within the model that you want to focus on. And so you can include one additional figure for that. Okay. All right. So this next part's important. So if you are taking this course for graduate credit, either you are a grad student, you are a master's student, or maybe you're an undergrad, you're taking it for graduate credit as well. There is an extra part of the final project that you have to do. So it is required that if you are going to take this course for graduate credit, that you do have to do an extra assignment. And the extra assignment for this course is a literature review. And so you're going to look up a paper, a scientific paper that has something to do with computational cardiovascular modeling. There's a lot that's out there, and you're going to write me a review of it, right? And so the review is going to be about 2-3 pages, single space with figures, okay? And you're going to submit that together with your final report. It's not extra credit, so it's part of. So if you're an undergrad student, you know, you don't have to worry about it. You don't have to do this. But if you're a grad student, then you do have to do this part of the project. Okay. All right. Any questions on any of this so far? Okay. All right. So let's talk about the final report components. And so, you know, the final deliverable that you're going to turn in is going to be the final report. Unlike the midterm project, I don't need your vascular files. So for your final project submission, you just have to turn in the report to me. So the report is going to be 12 to 15 pages, although there is no strict requirement, and so I'm not counting the pages or anything like that. What I'm more interested in is the content of the report, right? And so depending on your model, depending on the you know, the complexity, you may have a longer report, you may have a shorter report. But as long as all the content is there and I feel that it's discussed in sufficient detail, then I'm not going to ding you for being under the page limit. But if you want an average, you know, most reports kind of fall into this range right here, 12 to 15 pages, and that includes figures. Okay. Okay. Yeah. Question.
Format you want us to follow, but
Yes. So I do have a template that I post online as well. It may not be there right now, but I will post a template for you guys to follow. Yeah. Okay. So the final report, you can consider to be basically like a technical report. So you can consider your audience to have, you know, sufficient technical information, so you don't have to kind of explain things from scratch. But I do expect things to be explained in sufficient detail. Okay. The analogy that I always tell people is that imagine that you're writing this report and you're trying to explain it to yourself, but before you took the course, right? So how would you kind of explain kind of what you learned in this course and kind of explain what's going on with your final project to someone like you who, you know, who has interest in biomedical modeling, but, you know, hasn't taken a course of this. Okay. All right, so the components of the final report are pretty standard. So you have an abstract that's pretty standard for a scientific report, introduction and background. And so this is where you're going to kind of maybe talk about some of the components that are in that PDF that I gave along with you guys for the midterm project. Talk about the nature of the patient, nature of the anatomy that you're discussing. You know, and maybe any kind of disease that's in your model. as well as just maybe what computational modeling is in general. Okay. Next, we have the methodology section. So that includes the your model and your mesh, right? So you've already done this, or for the most part, you guys have already done this. So you've already created the geometric model. And so you're just going to summarize kind of the components of your midterm project in your final report. Okay. Because if you notice for your midterm project, I didn't require any kind of report or any kind of explanation, but you are going to have to write about it in your final report. Okay. All right, and then your results, and then so for your results section, I've already kind of outlined what I want for the results section. That's kind of up here. So I want a pressure plot. I want a wall shear stress plot, velocity streamlines, and one other figure. And I want you to answer all of these kind of discussion questions in the report as well. Okay. So your results section is pretty much laid out for you, right? Most important thing, there are a lot of figures that I am expecting on the report, but I don't want you to just put the figures, right? And so just like any scientific report, it's more than just a bunch of figures. You have to kind of explain what's going on. You have to discuss the results, okay? And part of that is answering the questions that I had posted earlier. And then finally, we have the conclusion. It's a conclusion, standard stuff. Okay, so I don't have it here, but of course, since the midterm project was individual, this is going to be individual as well. You're going to do it on the exact same geometry. And so, feel free to work together in terms of, if you guys are having issues or with the program or setting up things, that I'm okay with, but everyone needs to do their own simulations. Okay. All right, any questions on the final projects? Okay. All right, so that's the final project, and so I don't expect anyone to really honestly I don't expect anyone to really get started in earnest until after the exam next week. We are going to do the workshop this Thursday, but I expect things to kind of pick up after the midterm next week. Okay. All right. All right, so let's go ahead and go on to the lecture for today. All right, so this week is going to be all about computational fluid dynamics, right? So I'm sure a lot of you have probably heard of it. Some of you are probably in 436, so you kind of already know what CFD is. So today's lecture is just going to serve as kind of an introduction to kind of what CFD is and in terms of what we can expect from it. But also in terms of what are some of the main considerations, what are some of the main parameters and values that we have to be aware of. Because the thing about CFD and probably if you've taken 436, this is that there are a lot of different settings that you choose for a CFD simulation, and it can honestly all sound like a foreign language if you don't know what those settings do. And so today we're gonna introduce this. What are some of the main settings that you're going to be responsible for, specifically for Cardiovascular, and then we'll put it in practice on Thursday. Okay. So what is CFD, right? So CFD stands for Computational Fluid Dynamics. And in short, what it refers to is using any kind of computer, specifically high performance computing, to simulate fluid. Okay. So you'll hear me use this term a lot, high performance computing. Well, another way you can abbreviate that is HPC. Okay. That's a very common acronym for that. Basically, high performance computing refers to using multiple cores to run a simulation. Okay. So a lot of the apps and a lot of the programs that you guys are probably used to on your computers, I consider those to be kind of single core applications, and so they only utilize one computing core in your computer at a time. But if you really want to utilize the power of your computer, you can parallelize it, and so you can use multiple cores at the same time. Okay. So for some high-powered kind of desktop applications or some high-powered kind of mobile applications that may involve using 2 or 3 or 4 processors at the same time. But for something like computational fluid dynamics, this is really high performance. And so we're talking about dozens or hundreds of processors at the same time. Okay. Now, of course, this can't take place on your standard computer. So even the most powerful desktop computers nowadays don't have more than 4 to 8 to 16 processors. And so most simulations take place on something called the supercomputer or cluster. That's what you hear called sometimes as well. Okay. So a supercomputer is nothing more than just a huge rack or a huge system of computers that are all kind of in one place that are designed to run kind of high powerful simulations like this. Okay. I think recently, supercomputers and AI has been, kind of pushed in the mainstream a little bit more recently with everything that has to do with like cryptocurrency and AI. So people are becoming more and more aware of it. But before the age of crypto and before the age of AI, we use supercomputers to do things like this, which is what I call kind of scientific computing. So there's kind of a long, well, at this point, kind of a relatively long history in supercomputing. Okay, and so the idea and the reason we use these computers is that to solve the equations of fluid flow, that's conservation of mass and conservation of momentum, doing this by hand is way too difficult. And so if we utilize a computer, which can run calculations at speeds way faster than humans, we can simulate very complex flow, right? So here, what I have on the right here is one of my more favorite images of CFD. Where basically these scientists have used CFD to simulate the airflow around an elephant, right? And so we have this kind of a computer representation, a CAD model of an elephant, very beautifully done, considering an elephant is a very amorphous geometry. So there was a lot of art that had to be done with this. And so, this is kind of a cool thing. So you can compute, what's the aerodynamic drag on an elephant as he kind of walks and gets water or something like that. Right? And so with CFD, you're able to simulate very complex fluid patterns on complex geometries that would otherwise be impossible to do, by hand. Okay. And there are a lot of softwares that do this. And so there are a lot of names in the game. And so I think this is another reason why people, I think, get confused with CFD. Because there's a lot of different programs. And so you have programs, ANSYS, that's the one probably a lot of people are familiar with. That's an FEA software. We have OpenFOAM. OpenFOAM is probably the biggest open source CFD project out there. That one is finite volume based. I believe that's the one that Dr. Myrell is using for 436. There's STAR CCM, that one is more specialized for aerospace applications. And Synvascular is also a CFD software. Although Synvascular is more specialized for blood flow. Okay. And so part of the reason you have so many different types of softwares is, well, honestly, a lot of people want to get the fame and glory. So everyone kind of writes their own code. It's kind of a hobby thing as well. But also, a lot of these programs are, they usually have very niche uses. And so the field of CFD is very large. And so you can do huge macroscopic flows in terms of things like weather model, right? And so you can use CFD to model kind of the weather patterns and wind patterns across entire continents, right? And so that's a huge scale flow that occurs over thousands and thousands of miles. Or you can use CFD to simulate flow in the smallest of places like blood flow, right? And so it turns out, you use, slightly different methods depending on the application, whether you're doing weather modeling or blood flow modeling, there's tiny changes in the methodology that you do. And so that's kind of what gives rise to lots of different softwares. So there's a lot of different softwares out there. There are some that are more used than others, but just know that, there's a lot out there to use. Okay. All right, so let's talk applications. So CFD can be used for a lot of different cases, right? Probably the most common place that it's used is in the aerospace industry. So designing, airfoils, designing rocket propellers, things like that, propulsion. Just aerospace, it just naturally fits really well with aerospace just because, everything, to fabricate anything in the aerospace industry costs a lot of money. And so there's a lot of simulation work that's done, before you move on to manufacturing, just to make sure your designs are sound and things like that. Okay. Weather modeling, just like I mentioned, and so you can do predictions of weather using CFD, depending on the wind patterns and the humidity and things like that. Okay. Industrial manufacturing, and so there's a lot of applications there as well. Biomedical, of course, that's kind of what we're doing here. HVAC, that's heating, ventilation, air conditioning system. There's a lot of CFD that goes on there. Thermal engineering. And automotive. I believe this image here, it's been a while. I don't remember exactly where this image came from, but it looks like kind of a manifold that came from a car or something. So lots of applications. Basically, if it has fluid flow, if it has liquid, it has air that's flowing through somewhere, you can model it with CFD. Okay, so how do you run a CFD simulation? And so, you know, of course, the exact steps, the exact buttons that you press are going to depend on whichever software that you're using, but the general steps are mostly the same between every software, right? It's kind of more how you achieve each of these steps. So I've kind of broken down into 7 different steps. And so step 1 is to define the problem. Step 2 is to model the geometry. 3 is to mesh. 4 is to apply the boundary conditions. 5 is to specify any parameters that you need for the solver. 6 is to run the simulation. And 3 is to post-process and analyze the results. Okay. So for your final project, you know, we've already done a few. We've already done a couple of these, and so you know we've already done the first 2 steps, right? We've done step 1 and step 2 already for your final project. And so for your final project, we're basically going to do step 3 and okay. And that's kind of what we're going to be talking about mostly for today. Okay, so let's start with step 1, defining the problem. And so, you know, it's the first step to running a simulation, but I think it's often the most either the most overlooked step or the most ignored step. And so definitely it's important. So your first step whenever you're performing any engineering analysis is to define the problem, right? So what are we analyzing? You know, what physics are relevant, what equations are relevant, what information do I want to get out, and what are the expected results, right? These are all questions that you should know the answers to before you tackle any engineering problem, right? So you shouldn't just be doing anything just for the hell of it. You know, you should kind of have some purpose to kind of, you know, doing what you're doing. All right. And so in terms of CFD, you know, the last 2 questions here are the most important to ask, right? Because running a CFD simulation, you know, it's, you know, nowadays it's not thought about nearly as much just because of you know, computers have gotten much stronger, but it is still a reasonably, you know, high investment to run a simulation in terms of computing power, in terms of electricity, and in terms of time, okay? And so you want to make sure that if you are going to run the simulation, you should know kind of what information are you going to get out and what your expected results are going to be. Okay. All right. And this is important because, you know, when you run your simulation, you know, it's very rare that you run a simulation and it works out perfectly the first time. In fact, if that happens, then I would be kind of more stressed than that, right? And so, you know, at least thinking about, you know, what are some of the expected results or what you expect to get out of the simulation, that's really important to know before you start so that when you get the results, you know how to kind of, you know, do a sanity check on yourself, okay? So for the most part, you know, for this final project, it's these questions are mostly answered for you, or they're answered within the project instructions. But it's a good practice. It's a good habit to get into in terms of asking yourself these types of questions. Okay, number 2, modeling the geometry. Okay, so this is what you guys did for your midterm project, and so you've all created a CAD model or a digital model of your geometry. Okay, the most important thing, and I think the thing that I think trips people up the most when they're running CFD for the first time, is that your CAD model, it should be of the fluid domain. Which is a little bit of a different mindset to, you know, when you think about typically how people use CAD, right? And it's typically when you use things like SolidWorks or CATIA, right? You're making a digital model of the solid part of your geometry, right? And so if you're modeling like a piping system, you know, you would make a pipe like this, so hollow on the inside, and you make, you know, a model for the walls, right? Because that's the solid part. But for CFD, you need to kind of invert this. And so what you need to actually model is you need to actually model the region where the fluid is going to flow, okay? And so I use this pipe as an example. And so, you know, for this pipe here, you know, if we want to run CFD on this pipe, we can't use a model like this because the middle is actually empty. And so you actually need to make a solid model of the part where the fluid flows, which is inside the pipe, okay? So it's a little counterintuitive at first because you look at this and you see a solid, you know, most people look at this and see a solid cylinder. And you would think, you know, how could fluid flow through that cylinder, right? It is flowing through the cylinder, but, you know, think of the cylinder as actually kind of the liquid part of your simulation, okay? Not the solid part. So the fluid's going to flow through kind of the liquid part here, okay? All right, so if you, when you're, in using Simvascular, we don't really have to worry about this because Simvascular just naturally creates that model for us. So you guys have already kind of done that already. And so if you notice about your midterm project, you've created a kind of a solid block model of the blood vessels. But we're gonna have fluid flowing through. Okay. So just kind of a small note here, just to, just not to psych yourself out that, what Simvascular is actually giving you is actually correct. Any questions on this so far? Okay, good. All right, next step is meshing. And so this is what we're going to start with on Thursday, right? And so the important part for any computational simulation, whether it be FEA or CFD, or finite volumes or whatever, right? You need to create a mesh for your model, okay? And so what a mesh basically is that you basically are going to take your geometry and then break it up into a bunch of smaller, simpler shapes, okay? Because most of the times if you're running a simulation, you're doing it on a geometry that is very complicated or complex. And so that's very difficult for computers to run simulations on. And so what you do instead is you break this up into a bunch of simple triangles and squares and tetrahedrons and hexahedrons, so that you can run your simulation, okay? So the reason this step is called meshing is that if you kind of visually look at a discretization like this, it's almost as if you put kind of like a wire mesh on top and you kind of wrapped it all. Okay. So that's where you get the name, okay? The exact name for this step is discretization. So you're discretizing the geometry into simple shapes. But just, meshing also just sounds cool, I guess. And so people just call it meshing. Okay. Okay. So the important thing to note when you're doing a mesh is to pay attention to the number of elements and nodes that comes out, right? And so depending on the size of the elements, and so how big you specify your elements, you could end up with a lot of elements and nodes or very few elements and nodes, okay? And this number is very important because the number of elements and nodes that you have, that's basically going to determine, the cost or how long it's going to take for your simulation to run, but also it's going to determine the accuracy as well, okay? And so there's this kind of inverse relationship. So the more elements you have, okay, so more elements, the cost is going to go up as well, okay? And so in terms of cost, I mean time, right? So time is money, right? And so, it could be the difference between waiting 5 minutes for your simulation and waiting 5 days, right? So there's a big range there. But generally speaking, the more elements you have, the more accurate your simulation is going to be as well. Okay? So the analogy that I always like to give people is to think of it like the resolution on an image, right? Or the resolution on a monitor, right? So monitors are always rated in terms of how many pixels it can show you at any given time, right? So the larger the amount of pixels, the more the higher fidelity that monitor is, and the more beautiful and crisp your images look. Okay, and so meshes are the same way. So the more elements that you have, the greater resolution that you have, the more crispy your simulation is going to look. It's going to make your result more accurate, but at a higher cost as well, right? And so if you want a really good monitor, you want a really good, 4K TV or something like that, you have to pay a lot of money for it. And so simulations are kind of the same. Okay. So I will tell you right now, so I don't have this in the slides, but probably the part of the final project that you will guys struggle with the most is the meshing, okay? So and meshing is kind of a step because I know some of you, were in my finite element class last semester. Meshing is a step that for the most part was fairly automatic. I know some people had some issues with their final project. But for the most part, ANSYS has a very strong mesher. And so basically you can throw any geometry at it and it'll produce a mesh for you. Okay. There's a reason ANSYS costs a lot of money, and there's a reason ANSYS kind of hides their secrets behind their software, because a lot of meshers aren't as robust as ANSYS. And so probably what you guys are going to experience. I tried my best to try to make it so that you don't experience this by having all those rules for the midterm project. You're probably going to have some trouble with the mesh. Okay. Now, if you did everything up to this point, well, your model has completely intersecting, has all your vessels intersect well. your model is relatively smooth, then hopefully you're not gonna have any issues with meshing, but that said, there's still some stuff, okay? So the main things that make meshing difficult is if you have any sharp corners in your geometry. For the most part, I expect most of your guys' midterm projects to have some sharp corners right now. That's totally normal. And so what we're going to be doing on Thursday is we're going to learn how to smooth the model. Okay. So I know you guys already, you guys probably already applied some smoothing when you did the segmentations, but there's kind of another layer of smoothing we can do on the entire geometric model to kind of make sure it's all, it's all good. Okay. So the more you smooth your model, generally the easier it is to mesh. Okay. The other thing that makes meshing really difficult is if you have very, very tiny surfaces. Okay. And in some vascular, the most common case when you have a tiny surface is if you have a vessel that's not intersecting properly, right? So if you think back to the midterm project, one thing I had you guys do was count the number of caps. And if you had an excessive number of caps, probably what's happening is that you have kind of an intersecting vessel that's not intersecting properly. And so you have kind of a tiny sliver of model that's coming out. So for the midterm project, it's not that big a deal. Your model still visually looks okay, but you are going to run into issues when you do the mesh. Okay. So there are ways around it. If your sliver is really, really tiny, there's ways that we can go around it. But honestly, a lot of times the best thing to do is actually to go back and kind of fix the model. Okay. So I expect the meshing is probably going to give people the most headaches. It's the most common email that I get for the final project whenever I teach this course. Maybe about 30-40% of students email me at some point saying that they can't mesh their model. And I expect those 30-40% to help another 30-40% in the class that didn't come to ask. And so, you're going to have issues with meshing. It's a given thing. Okay. In fact, if you don't have issues with meshing, then you are a modeling savant. And some vascular, if we ever make a company out of it, we'll look to hire you for sure. Okay. Any questions on meshing? Okay. Good. All right. So the next step that we have to do before we can run a simulation is to apply the boundary conditions. Okay. And so, at this point, after you have your mesh, the simulation is more or less ready to go. Okay. And so at this point, what we're going to be doing is we're going to be asking the computer to solve the governing equations on our mesh, right? So for each element. But in order to solve our equations, we need to know kind of what the solution looks like at all the boundaries of our domain. Okay. And that's what it means to apply boundary conditions, right? So for every exterior boundary on your model, and so that includes all of the caps, right? As well as the wall, right? We need to specify something on these surfaces in order to solve our solution. Okay. So for the walls are very simple. And so for the walls, what we're going to be doing for this project is we're going to be doing a rigid wall simulation. Okay. And so we're going to specify 0 velocity at the walls, and we're going to assume that the fluid is going to slip or no slip at the wall. It's going to stick there. Okay. So the walls are very simple. It's the inlets and outlets that kind of need a little bit more discussion. Okay, so let's talk about the inlet and outlet boundary conditions, right? So the inlet boundary conditions are basically the portions of your model where the flow is going to enter your geometry. Okay, so for most of your models have only one inlet. Those of you that do cerebral models, you may have 2 inlets, but for the most part, most people have one inlet. For those of you doing congenital heart disease, you may have 2 inlets in your model as well. But for everyone that's doing an aorta model or aorta femoral model, you'll have just 1 inlet to work. Okay. And so for the inlets, we need to specify basically how much blood is coming into the domain. Okay. So that's kind of what this indicates here. So at our inlet, we have all these arrows coming inwards. So that's all the blood that's coming into our domain. Okay. Okay. And then for the outlets are the portions of the geometry where the flow is going to exit your domain. Okay. So those are all basically all the other caps of your models, right? So what we'll do, and we'll do this in the workshop on Thursday, is that for your model, we'll identify which cap is your inlet, that's where the blood's coming from, and we'll identify which caps are the outlets, that's where the flow is going to exit, okay? All right, so typically speaking, when you're running a CFD simulation for all your inlets, usually the most standard way to set it up is you have a Dirichlet boundary condition there. And so in other words, you're specifying the velocity or the flow at the inlets. And then for the outlets, you prescribe a what's called a Neumann boundary condition. And so that's typically like a pressure type of boundary condition. Okay. There are ways to set it up besides this, but this is usually the most stable setup for running CFD, at least in the world of finite element CFD, which is kind of what we're doing. Okay, so next let's talk about the wall boundary conditions. And so for the inlet outlet boundary conditions, we'll talk about this a lot more on Thursday as well. But I just want to give you a primer for today. Okay. For the wall boundary conditions, we're just doing something very simple. We're just specifying a no slip boundary condition. Okay. So we're basically doing this. So we're saying that the fluid layer right next to the wall is going to stick to the vessel wall and it's going to have zero velocity. Okay. So that is the very common no slip boundary condition. So that's all that's required. So for the final project, you just have to do a rigid wall simulation. Okay. Now with Vascular, it is possible to do a deformable wall simulation, and so you can simulate a moving wall, which is super cool. But it is very difficult to set up, and so it's not a requirement for the final project, but you are of course welcome to try it. And if you do it, then you will be rewarded with a very cool looking animation at the end. But it is tough to set one up, so I'm not requiring it for the final project. Okay, all right. So next we have solver parameters, and so these are parameters that you have to specify in the solver. Okay. So these are kind of more solver specific. So these are often kind of, oftentimes if you run a CFD software, you have a lot of different options for these. And so it's useful to know kind of what each of these mean, or at least what some of the main settings are. Okay, so the first one that you're going to specify are the fluid properties. And so we have to specify the density and viscosity of the blood. So that's pretty standard. You need that to solve the equations. Next, we have the time step size. And so the time step size is the separation between successive solutions. Okay. So the way the CFD is going to work for a time dependent solution, you're going to be solving for the solution at discrete moments in time, right? And so you can see this timeline kind of illustrates this. And so in this timeline here, we're solving for the solution every 0.1 seconds, right? And so our time step size in this case is 0.1 seconds. Okay. So basically, you're going to start from an initial condition and you're going to solve the equation of what the fluid's going to look like 0.1 seconds in the future. Okay. Then you're going to go from there. You're going to solve, from here, if we go 0.1 seconds in the future, then we're going to solve for it. That's what the next solution is going to be. Okay. And so in order to set this up, you need to specify what the size of this time step is going to be. Okay. So for you guys, for the final project, most cardiovascular simulations work on relatively the same time scale. So usually the best time step size in that case is 1 millisecond. So we're talking 0.001 seconds. Okay. So things, so usually you set your time step size to be about, just to make sure you can capture all of the information in your simulation. For cardiovascular flows, basically nothing happens faster than a millisecond. And so a millisecond is kind of the perfect amount of time resolution that we need. Okay. Of course, you can set this smaller, right? And so if you want a super resolved simulation, so you can make it smaller, like 0.0001. Okay. And there may be applications where you have to do that. But of course, making the time step size smaller is also going to make your simulation more expensive as well. Okay. So it's kind of one thing to keep in mind. So usually a good balance of kind of performance and speed is 0.001 second, which is 1 second. Okay, another thing that you're going to specify is the number of time steps, right? So each time your simulation kind of moves forward by a time step, that is considered one time step. Okay. And so to run a full simulation, basically you're going to be solving for the solution for a certain number of time steps. Okay. So normally the way to set this is that you kind of beforehand, you kind of specify how long you want your simulation to simulate. Okay. So I'll give you an example. So for a pulsatile simulation, and so and you're going to be doing this for your final project as well, okay? Usually for a pulsatile simulation, you want to simulate 6 pulses, okay? So that's 6 heartbeats, okay? The reason for that is that, you know, there are a lot of kind of transient effects that occur during the first couple beats, and so you want to make sure that you kind of reach steady state, okay? So you want to do 6 pulses. Each pulse or each heartbeat takes place over the course of 1 second, right? So your heart beats, you know, for the average person, you know, once every second, right? So that's 60 beats per minute, right? So to simulate 6 pulses, that means our simulation has to simulate a total of 6 seconds of time, okay? If our time step size, you know, if you think back to the previous step, if our time step size is 1 millisecond, so 0.001 seconds, okay? In order to reach 6 seconds, right? How many time steps then do we have to simulate? Right. So we take the ending time, we divide it by the time step size like this. Okay. And in that case, we end up with 6,000 time steps. So for most of you, you know, for your final projects, you know, I'm going to recommend that you simulate, you know, 4 to 5 to 6 pulses. So your pulsatile simulation is going to be in that ballpark of 4,000, 5,000, 6,000 time steps, okay, depending on your time step size. Okay. The next setting that you need to specify, so not every software has this, but it is a setting in Computational, is how often do you want to save your results? Okay. Now that seems kind of like a you know, kind of like a silly kind of setting, right? Because we're solving, you know, let's say we're solving 6,000 time steps, right? Right. We're doing the work of simulating 6,000 time steps, or at least the computer's doing the work, right? And so kind of the natural thing is, you know, we should save our results for every 6,000 time steps, right? So that's 6,000 slots for the results, right? Oftentimes this is a little bit overkill, right? So you don't want to save your results too much, right? Because if you save your results, right, you can think of that's your entire model, right? Your entire you know, anatomical model. Okay? And that's not only pressures, but also velocities and shear stresses and whatever other outputs that you're specifying for your simulation, right? Times however many nodes that you have in your mesh. So let's say you have a 2 million node mesh, right? Okay. And so you have 2 million nodes. And so let's say that you have, you know, let's say you just even have just the basic results, which is 3 components of velocity, XYZ, pressure, as well as wall shear stress, which also has 3 components, right? So that's 8 components of results. Okay. So you're talking 16 million pieces of data. Okay. And if you save that for all 6,000 time steps, you're going to multiply this by 6,000. Okay. So that's a lot of data, right? And of course, you know, all of it is stored in the computer, but even your computer has limits as well, right? And so if you're a little bit too gung ho, if you're a little bit too you know, save happy, you could actually run out of memory for your simulation, which you know, not the worst thing. There are safeguards that we have on the cluster to prevent that, but you know, at that point you've kind of wasted, you know, a couple hours of your time, right? And so you usually don't want to save every time step. Usually for you know, for a CFD simulation, you know, I would say every 50 time steps is usually pretty sufficient. And that kind of gives you a good balance of, you know, giving you enough, you know, time resolution to be able to see everything that's going on, but not kind of overloading the file system or overloading the memory with all of these results. Okay. You have to be careful of this because, you know, you know, that supercomputing gateway that I mentioned, that, you know, that's kind of something I do on the side. I kind of manage that gateway. I've had a lot of issues recently because some users were kind of a little bit too safe happy. And so they're taking up several terabytes of data on the cluster. And I got a lot of angry people yelling at me this semester. So, you know, I can blame people when they're not my students and say, right, oh, you know, they didn't know. But you guys are my students, so you guys can't make that mistake. I don't want to be yelled at more than once this semester by because cluster people are scared. Okay. All right. And so the last thing that you need to specify here are linear solver tolerances. So that controls that has some controls about how the solver performs. For the most part, we're using standard. We're going to use standard settings for that one. But getting into the discussion of kind of what that actually means is a little bit tough. Are you guys going over linear solvers in 436 as well?
Has to do with how many iterations before you converge.
Yeah. Okay. So you guys are exposed to it a little bit. So it is a little bit advanced. So I don't want to get into it in this class, but we're just going to use kind of fairly standard stuff. All right. Any questions on this here? Okay. Good. Okay. So the next step is to run the simulation, right? So you've done all the hard work. You've done all the meshing. You've done the boundary conditions. You've applied all the settings. Now you can kind of sit back, right? And so running the simulation, what that basically entails is, taking your simulation job, taking your mesh, shipping it off to some supercomputer, and then letting the supercomputer do its thing, right? And so at this point, you can get up, you can get a snack, you can go to sleep, you can, go take a dump, whatever, right? So the computer's doing all the hard work for you. Now, of course, your simulation could fail, right? So there are cases where, maybe you didn't set things up properly. And so I expect, it may take several tries, so don't expect the simulation to work on the first try that you do it, okay? But in theory, we've set up these clusters are set up so that you can just submit a job and then come back and get the results, okay? So depending on the nature of your job, depending on how expensive it is, it could take, your simulation could take anywhere between a couple minutes. So the simulations we're going to do on Thursday are going to be fairly light, and so you can run all of those on your personal computers. But some simulations of very heavy phenomena. So this is like the weather forecasting and turbulence simulation. I've seen simulation take several weeks of just constantly running, and that's using thousands of processors too. So there's a huge range in how expensive these simulations could be. We're definitely on the lighter side, so blood flow simulations are definitely fairly lightweight simulations. They are still, a little bit too expensive for your own personal machines, but they're very light compared to some of these bigger ones. So just know that there's a huge variability in this. Okay. Okay. All right, and then after that, then last step, technically your simulation is done. And so the next step is to get your result and to post-process. And so at this point, you'll have results in terms of what the pressure looks like, what the velocity looks like, the flow rates. And so now is the time to kind of plot your results, so you'll be able to generate a lot of pretty images like this. Okay. So this image here, you can see that what this person did was they plotted the velocity profile at different points along the vessel. Okay. So we can definitely make plots like this as well. So this is something that you could show in your final report. Okay. And you can analyze your results. So that's the most important thing. Okay. So remember, like we talked about at the beginning of class today, this class is more about than just running the simulation and generating the pretty picture. But you also should be able to kind of discuss your results, discuss the pressures, discuss the wall shear stress, and relate that to kind of what your project is all about. Okay. And so it's at this point where you kind of do your sanity check in terms of, did you get what you're looking for? Do your results make sense and what? Okay. It's really important for this step to look at your simulation and kind of ask yourself if the results you're getting are making sense. Because I'll tell you right now that probably most likely that even if you get a simulation to run on the cluster, you're going to get your results and your results may not make that much sense, right? And so it's important to kind of look at your results, maybe send them to me. We can talk about them, and then we can go from there. All right, and so that is the process, right? And so we're going to be going through all of this on Thursday. Okay, so the last couple of slides here are just kind of general information about high performance computing, that you can kind of take to your next thing, right? So of course, high performance computing, HPC is not just limited to just blood flow simulations. We use HPC for so many different applications nowadays. There is a constant growth of computing power. It's kind of amazing, how far we've come in terms of computing power in kind of such a short amount of time. I was talking with some of you guys might be a little bit too young for this, but I remember strictly growing up and we were struggling to even get on the internet without using like a dial-up modem, right? And so I remember, if I wanted to go on AOL or something like that, we'd have to, plug in the modem, disconnect the phone, dial in a couple times, and then, that's only so you can load just some text from AOL.com, right? And now that's child's play, right? And so, and even if you look at, a lot of our entertainment, right? And so, if you think back to a movie like Toy Story, right? Toy Story was one of the very first kind of computer graphics movies. At the time, it was amazing, right? So there was nothing like that in the world, just because, it was before that, computers couldn't do anything like that. Now, if you look at Toy Story, Toy Story looks like shit compared to, all the modern kind of animation movies we have, just because computers have just gotten so much better, right? So it's kind of scary that, in such a short amount, even in my own lifetime, I've kind of visually seen just how far computing has come. And so, it's crazy to think about what's going to be possible in the next 10, 15, 20 years. Especially as things like AI comes into effect, right? But generally, if you're talking HPC, most people think about something like this, right? So this is kind of a server room. So this is kind of one of the more, it's one of the more visually appealing ones. So I think this is an IBM machine. So I think it's Blue Gene. Yeah, it's Blue Gene. So basically a cluster is something that looks like this. So it's a server room where each of these kind of, we call these kind of a racks. Each of these kind of houses, a big computer, right? And so when you put so many of them together and they're all connected through the same kind of modem and router and things like that, this is kind of what constitutes a supercomputer. Okay. So of course, not everyone can have these. If you have one of these in your basement, you're probably on some list from the FBI. So these are only kind of located in specific areas. So a lot of times, the government usually funds these HPC clusters for community use. Okay. So that means that, most people access a cluster through a remote kind of system, right? And so they use the internet to send their data, they send their simulation over to the cluster, and the cluster runs the simulation. And then after it's done, then you download it back. Okay. And so, and there has to be kind of a dedicated room for these. And so the cluster that we're going to be using is actually fairly close by. It's in San Diego. So on the campus of UCSD, there is called the San Diego Supercomputer Center. So that's SDCC. Their machine right now is called Expanse. And so we're going to be using that machine. But I've run simulations on machines in Texas. There's a few huge machines in Texas. There's some on the East Coast, New York, things like that. Okay. So as computing gets bigger and bigger, you see more clusters like this pop up. Okay. Cal State Fullerton, we do have a cluster. It's actually not in the engineering school; it's in the NSM building. But it's aging, so it's a little bit older. So we're going to be using kind of a newer system in San Diego. Okay. So traditionally, to access a supercomputer, you have to access it through a Linux terminal or command line terminal. Just because these systems, just so that, just to kind of maximize the amount of power for the computing, they have very, very simple graphics capabilities, if any at all. And so there's no kind of Windows, there's no desktop, anything like this. It's all command line based. And so to access it, you have to also use command line. So we're not going to be doing that. We're not going to be learning Linux in this course. So what I've done, one of my kind of bigger projects is I've built this gateway, which is kind of like a web interface that kind of goes on top of the cluster. So you won't see this, but if you are interested, there is a lot of really interesting cluster stuff that you can do as well. Okay. Okay. All right. So the most important point that you guys will have to specify when you are using the cluster is you have to decide how many processors or how many computers you're going to devote to a single simulation job. Okay. And so the power of the cluster is that, the cluster that we're using, I think in total has about, it's been a while, I think it has around 200,000 cores in total. So it's a massive machine, right? So of course, we're not going to use 200,000 cores for our jobs. But you have to think about how many processors that you're going to devote. Okay. You always have to remember that the cluster is not for single use, right? And so we're sharing that resource with, not only are you sharing the resource with everyone in the class, but we're sharing the resource with, a bunch of other researchers and students and educators, throughout the nation and throughout the world, actually. So, you're going to have, at any given time, you're going to have thousands of different people kind of accessing the cluster and trying to run simulations. Okay. And so just like any other shared resource, just like, if you were to use the elevator here, or if you were to use the stairs or the train or anything like that, there is some etiquette and there is some kind of, rules to using it so that it's kind of fair and good for everyone to use, okay? And so generally what that means is to not hog up the entire cluster, okay? And so, you want to make sure that when you're deciding how many processors that you want to use for your job, you want to devote an appropriate amount of processors, okay? Now the tempting thing is to use a lot of processors, right? Because generally the more processors that you have, it's going to cut the amount of time down, okay? And so as an example, if you have a simulation, so let's say that you ran on 24 processors before, and let's say that it took, I don't know, 15 hours, okay? If you use 48 processors instead, it's going to cut that time in about half. So it usually doesn't cut it exactly in half, so it'll probably be around 8 hours instead. So it's a big difference, right? So the more processors that you use, it reduces the time, okay? It is possible though to actually use too many processors, right? So have you guys ever heard the saying of, having too many chefs in the kitchen? And so the exact same thing applies for processors as well, okay? So when you're running a high performance computing job, basically what's done there is that you basically take your mesh and you kind of split it up into all the different processors, okay? You want to make sure that each processor actually has enough work to do in order to make it effective, okay? Okay, so to give you an example, let's say that you are catering an event, right? And you have to prepare 100 sandwiches for the event, okay? If you have one chef, right? That one chef is suffering, right? Because that one chef has to make 100 sandwiches, right? If you increase that, so if you instead of one chef, you have 10 chefs, that makes the work a lot easier, right? So instead of having one chef prepare, 100 sandwiches, you have 10 chefs each producing 10 sandwiches, so you can work in parallel really well, okay? But you can't have too many chefs, right? And so if you have 1,000 chefs, right, that does not help at all because, you're going to have, it doesn't take 10 chefs to make one sandwich, right? And so you're not going to have, it's not going to speed this up by, 100 times. So there's a balance. So there's an optimal amount of chefs that you can assign to the job to get it done in the most time efficient way possible. Okay. So for simulations, for Simvascular, the number of processors that you specify depends directly on the number of elements. And so like I mentioned, when you run a simulation on the cluster, it's going to take your mesh and it's going to assign a certain number of elements to each processor. Okay? And what I found that with Simvascular is that if you have about 20,000 elements per processor, that's usually a good amount of work for each processor to do. Okay. And so to find out the number of processors that you should use, you should take the number of elements and divide it by 20,000. Okay. So for example, for a lot of your projects, you're going to have element counts in about 1 million. Okay. So that's 1, 0, 0, 0, 0, 0, 0. Okay. You divide this by 20,000. So 4 of these zeros are going to cancel out. Okay. 100 divided by 2. So this is about 50 processors. Okay. So of course, that's way more processors that you have on your own personal machine. But 50 processors on a cluster is a very modest amount. So this is a good amount of processors. Okay. All right. Any questions on that? Okay. All right. So we'll end a little bit early today. So I don't have the workshop ready. So when we come back on Thursday, question.
It's just on average, like how long are these take for these projects? Like,
So you're going to run 2 different types of simulations. You're going to run a steady state simulation. That one's pretty fast. So that one on the cluster will probably take no more than 10 minutes, I'd say. For your pulsatile simulation, that'll take maybe about an hour or 2. Yeah, so it's still pretty short. Yeah, not too bad. All right, so we'll come back on Thursday. I'll have the workshop ready for you guys. If you want to do the workshop, if you want to apply that directly on your project, you're welcome to do that. But I am going to provide you with a sample projects on Thursday as well. So if you want to just kind of follow along exactly what I'm doing, you can do that. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you all on Thursday.
I saw.
It's fine. No, he wanted to watch it. I'm gonna be sure that we don't have under.
You know, that was the guys.
He's in front of this paper though.
What was his son?
Sure. Got it. It's like, yeah. They're late.
That's what
Yes, yes. I'm going to photo machine.
Not that that's what to me.
No, please.
Why are you going back to season one? Yeah. They also need to give hidden that piece.
No.